Hello, hello, hello. This is Nicholas on this lovely Tuesday afternoon. Having a question for you first. What do you call a 3.14 meter long snake? Well, the answer is a python. Anyways, I'd like to talk to you today about kind of generalizing implicit differentiation and some neat tricks that usually go overlooked in a single variable calculus course. So we have, usually we do an example with a circle, right? So on the one hand, like let's say we have x squared plus y squared equals 25, right? A circle of radius 5. Now, as it's written right now, y is implicitly a function of x. In other words, we don't have y equals f of x. We don't have that, right? But we can get it in that form pretty easily because y is equal to plus or minus the square root of 25 minus x squared, right? Solving for y there. And so on the one hand, you can differentiate this to get dy over dx, or you can differentiate this and use the fact that y is a function of x, and then when you differentiate that, you get 2y dy dx, and you can solve for dy over dx algebraically there. So that's all kind of review from Calculus 1. Now I want to turn to a neat trick that's mentioned in multivariable calculus using partial derivatives for implicit differentiation. So the way we really think about it is, so we have a function f, and what we're going to do is instead imagine f, right? Normally we have y equals f of x. A single variable function, we have y equals f of x. What we're going to instead imagine is that this here is a level set of a higher dimensional function. So we're going to make this f of a different capital F of x comma y is equal to some cross section at z equals c, right? In other words, it's set equal to a constant on one side. So on the one hand, y equals f of x. On the other hand, f of xy equals x squared plus y squared equals 25. So we can view this circle in 2D as just, well, a circle, or we can view it in 3D as a cross-section of the paraboloid by the plane z equals 5. So this parabola is going up like that, but its cross-sections, I'm sorry for this awful drawing, this cross-section on this plane here, z equals 5, gives us that same circle. So we're going to choose to think about the 2D function as a higher dimensional level set. And you'll notice that this is going to be very powerful because now what we can say is we kind of imagine a tree of like functional dependence, right? So f, capital F, is a function of y and x. And then in 2D, right, y is thought of implicitly as a function of x. So what we get is that the partial of f, if I differentiate this here on both sides with respect to x, I get the partial of f with respect to x plus the partial of f with respect to y times dy over dx equals 0. And this is so because of the multivariable chain rule, right? I look at this tree, I say, I'm differentiating this with respect to x. So I say, okay, well, on which branch can I go? I can go like that. I get the partial of f with respect to x. Or I can go like that, get the partial of f with respect to y. And then once I'm at y, there's only one place I can go, which is to x. And so therefore, it's a single variable ordinary derivative dy over dx. And then so solving for dy over dx, we get that that's equal to negative the partial of f with respect to x over the partial of f with respect to y. And this is the Nito theorem that is often overlooked in Calculus 1, and I guess rightfully so, because who has the background on partial derivatives at that point? But so if we think about finding dy over dx using implicit differentiation the normal way, right? We get 2x plus 2y dy over dx equals 0. And so dy over dx is equal to negative x over y. But let's think about that same circle using this trick right here. So if I say that dy over dx is equal to the negative of the partial with respect to x. So really I have to bring this 25 over to the other side to get x squared plus y squared minus 25 equals 0. And now the partial of f with respect to x of all of this, well, that's just negative 2x. And the partial of f with respect to y of all this is just 2y, aka negative x over y. And we get the same thing. Now, in this case, it was a very simple function, so it really wasn't much work one way or the other. But in the long run, this is so much easier. Now, I want to specify one condition here that will lead us to the multivariable implicit function theorem. So if I notice this right here, dy over dx, right, I have to realize that this is true provided that the partial of f with respect to y cannot equal 0. And on the one hand, we can view this algebraically, right? We can't divide by 0. But on the other hand, there's something much more geometric about this condition right here, the partial of f with respect to y not being equal to 0. So if I draw this circle, right, it looks like that. Now, when we're viewing this function here as a level set of a higher dimensional function, then that means that we can talk about the gradient of f, which is always going to be perpendicular to, and I'll just write the level sets, right? Because we established that the directional derivative for a given velocity vector of the function at a point, for real valued functions anyways, is equal to the gradient of f dotted with that vector v. The functional output isn't changing, so the directional derivative is 0 for any velocity vector. And so we get 0 is equal to the gradient of f dotted with the vector v, and therefore the gradient is perpendicular to any tangent vector at that point. In other words, it's perpendicular to all points on the level set. So if I picture the gradient, say, at this point right here, the vector will point like that. Now, something that's overlooked here is we only can do implicit differentiation when y is locally a function of x, right? So what that means is, let's choose a different point, say right here. Well, at this particular point, y can be viewed locally as a function of x. Remember, in order to see this, at least in 2D, we do things like the vertical line test, right? Now, in general, right, if we're talking about this circle globally, in other words, the whole circle, at this green point, right, y is not a function of x, right? It hits the vertical line twice here. But that really doesn't matter, because the game that we play is we say, okay, well, let's chop off everything else on the circle here except for just the bit around which we need. And now this is really not quite so rigorous, and you can define more precisely what it means for a graph to be locally a function, but not globally. But in essence, this is the intuition behind it. You chop off everything except for like just around the green point, right? And if you're just talking about around this green point right here, well then yeah, y is locally a function of x, right? Because it doesn't hit the vertical line twice, because this point here, we're just throwing out. We're just saying it's not existing. And it's really not relevant to our question of, well, what's the slope of this line right here at that point? So that's what we mean when we say it's locally a function at that point. Y is equal to y of x. Y is a function of x. Now, what's different, though, about this particular point right here is that the nature of the curvature at that particular point makes it so that no matter how much of the graph we chop off, right? If I'm going to get closer and closer and closer to chopping off that black point right there without actually chopping off the black point, I'm still going to be failing the vertical line test, right? you're always going to get a totally vertical line with an undefined slope. And if you go a little far away, right, you're going to hit a point here and a point here, a point here and a point here. You're always going to be hitting 2 points. You're always going to be failing the vertical line test. And at this particular point, there is no way, there's absolutely no way, locally or globally, that at that point, y just simply cannot be a function of x. So it does not make sense to talk about dy over dx at that point, right? At the point 5, 0. And we also see that algebraically from the fact that dy over dx was negative x over y. And likewise, the same thing happens at this point right here. But so another way to think about this is that, well, if we have a point where the curvature is like this on the graph, then that means that we have a vertical line with a slope kind of like infinity, in other words, undefined. But if we've got a vertical line here, what's perpendicular to a vertical line? Well, a horizontal line. And this horizontal line, the vector lies on that horizontal line. Which vector? The gradient vector. So the gradient vector is just, in this case, it's the partial of f with respect to x, partial of f with respect to y. And so if the gradient vector is perpendicular on the level set, then at that point, that means that it's flat, right? Because if we have a point that can't be viewed as a function of x, locally even, then that means that we have a flat gradient vector. And what does that mean if we have a flat gradient vector? There's no y component. In other words, the partial of f with respect to y has to be equal to 0. So there's two ways to view this condition right here, as an algebraic statement, just not dividing by 0, and also in terms of local and global viewing of a function of y in terms of x, or a function of x in terms of y, either way. So you can generalize this, right? If you've got a function like, I don't know, something crazy like x, y, z squared plus sine of x, y, z squared equals 0. And you want to talk about finding like the partial of z with respect to x. Well, the one thing that you just have to check before, let's say at the point at the origin 0, 0, 0. That just makes things nice. Well, the one thing you just have to check there is basically you first have to find the partial of f with respect to z. And in that case, that would be 2xyz plus 2z cosine of xyz squared. And you'd plug in 0, 0, 0, and you'd get 0. And that's not good. That means at the origin that the gradient vector, right, it has no z component. And so that means that at the origin, you simply cannot view z as a function of x and y, locally or globally, at that particular point on the surface that is defined by that level set. So we can't even talk about finding the partial of z with respect to x because the gradient is flat. And so therefore there's a vertical plane, just like how there was a vertical line test in 2D, there's a vertical plane that is totally vertical. Now, if it's just non-zero, then we can just proceed like normal, and we can view z as a function of x and y, and then just use the multivariable chain rule, just like how we use the single variable chain rule right here to find d or partial z with respect to x. So the multivariable implicit function theorem is very much similar. It just is a matter of noting the condition that the graph cannot be locally or globally a function of whatever other independent variable you're talking about. And so I believe with that,